Hello, this is Dr. Viv. Let's discuss two-dimensional and three-dimensional motions. In specific example of that is projectile motion. So in general, what we are looking for is a description of a point P that's moving in space in two dimensions in this case. At any given time, the particle's motion is being tracked by the position vector r that makes a certain angle with the positive x-axis, which I'm calling alpha. Now, in the ways of writing vectors, r can be described in two dimensions either as a ordered pair, x comma y, or you can describe it in terms of the Cartesian coordinates x I hat plus y j hat. Now if you were looking at three dimensions, you will have x comma y comma z, and r would then become x I hat plus y j hat plus z k hat. Other than that, there is no further complication to three dimensions compared to two dimensions, so we will stick with two dimensions for the rest of this video. This is known as the position vector. Now when you studied basic one-dimensional motion, I said the velocity can be got by position by differentiating. Well, that's also true in two dimensions. So the velocity vector v is just dr by dt, and the acceleration a is dv by dt. Everything that's true in one dimension continues to be true in more than one dimension. So we can do the differentiation. Velocity then would be equal to, I'll use this notation rather than that notation. So I'm going to get dx by dt, comma dy by dt, and the acceleration would be equal to d2x over dt squared and d2y over dt squared. So this is our x and y component of the acceleration, a sub x and a sub y. Now I should remark that there are other things going on in this diagram. The tangent to the position vector is the velocity vector at any given time, and the acceleration vector is actually pointing somewhere here. In keeping with the notation in UP1, we will use double shafted arrows to indicate the acceleration vector. Now if you look at this diagram, you can have separate descriptions of x and y. So that's going to be our line of attack. Rather than think of r of t, we're going to look at x separately and y separately, and then put them together if necessary to find out r. Let's talk about an important kind of motion known as projectile motion. A projectile is any object that's thrown in two dimensions, and we'll stick to two dimensions. In general, the projectile can also go in three dimensions. We assume that gravity is constant, and that is generally true if you don't travel too far from the Earth's surface. And for the case of simplicity, we'll have no air resistance. And there are more assumptions which I'll mention, but I won't write down, such as the Earth is not rotating and so on. Keep things simple. The Earth is flat. Not a very safe thing to say out loud these days, but we're going to assume the Earth is flat for this exercise. So let's do the case of projectile motion. Projectile motion has no acceleration in the x direction. Because there is no air resistance, there is no resisting acceleration in the x direction. In the y direction, there is just the acceleration due to gravity, which I will call negative g sub e, where g sub e itself has the value 9.81 meters per second squared. This value of course varies from point to point. So we have a complete description of our acceleration vector. Let's write it. The acceleration vector A is 0, negative g sub e. Now what we can do is, once we know the acceleration vector, we can find everything else by integrating. So to go from acceleration to velocity, I have to use velocity is the integral of a dt. Now observe, all these things are vector equations. So I can write the velocity v equals, when I integrate, I'm going to get the integral of 0 dt and the integral of negative g sub e dt. Well, the integral of 0 is just a constant. That constant is the initial velocity in the x direction. When I integrate g sub e times dt, I can take the negative g sub e outside, and integral of dt is just t, along with the constant, which is the initial velocity in the y direction. When I further integrate, I get the x coordinate. I won't bother writing this intermediate step, but the x coordinate will be the integral of that. So I'm going to get x naught plus vx naught times t, and when I integrate this, I'm going to get y naught plus vy naught t minus 1/2 gt squared. This would be the vector r, not x. So that completes the description of projectile motion. From this point onwards, it's just different problems. So let's work out a simple problem taking a specific case. So here's a cliff. Let me call the height of the cliff capital H, and I launch a ball, meaning I just throw it. The ball is thrown with an angle, initial angle theta. So this ball is going to arc nicely in the air and eventually hit the ground. Well, I would like in this problem to find out this distance d, that is how far away it is from the cliff when it reaches the highest point. And I would also like to find the final velocity v sub f with which the ball hits the ground. Those are my two aims in setting up this problem. Now I'm going to go about solving it. To find out anything about the highest point, you have to realize that at the highest point, the y component completely disappears and you're just left with the x component of velocity, which is vx naught. Now if you look at the x component of velocity, it never changes because time is not a factor. Whatever it was initially, it will continue to be the case throughout. Only the y component changes with time. In other words, it keeps decreasing. It decreases all the way to 0. That's when it reaches the highest point, and from 0 it starts building up in the negative direction because of the minus sign. So the y component changes, but the x component remains the same. So the condition that we have to impose to find the highest point is just that you set the y component of the velocity to be 0. Well, v sub y is all of this. So that tells me that vy naught minus g sub e t must be 0. So this tells me that t is equal to vy naught upon g sub e. So that gives you the time taken to reach the highest point, which I'll call t sub h. Okay. Now the distance x at the highest point, which I'm calling d in this figure, can then be found using this equation, this portion, because the x component of r is what we are looking for. So this is r of t, and the x component of r of t is precisely d. Well, that x component is x naught plus vx naught times the highest time. Initial x naught is 0 because the location of the projectile at time 0 is x coordinate 0, y coordinate h. By the way, the location at the final point is x coordinate something, let's just call it d, y coordinate 0. Well, this gives us vx naught times vy naught divided by g sub e. So that's my answer. Well, before we box this answer, let's try to figure out what vx naught and vy naught is. V naught is there, so vx naught is going to be v naught cosine theta. Vy naught is going to be v naught sine theta. And the two v naughts combine, so we can write this as v naught squared cosine theta sine theta divided by g sub e. And that is our answer to the first part of the question, which is how far away it is horizontally at the highest point. The second thing we have to figure out is what the velocity is. To find the final velocity, we need the final time. So that's the next thing we need to do. At the end, the projectile bites the dust, which means the y coordinate is 0. So we have to set this entire thing equal to 0. So at the final time t sub f, I'm going to get y naught, which is the initial height, plus vy naught t minus 1/2 gt squared. This is none other than a quadratic equation of the form 0 equals c plus bt plus at squared. Now, in high school, you've studied how to do this using the quadratic formula, and that quadratic formula is the following: t equals negative b plus or minus the square root of b squared minus 4ac over 2a. I'm sure you were singing it along with me. Okay, now let's substitute all these values. B is vy naught, c is h, and a is negative half g. So I'm going to get negative vy naught plus or minus square root of vy naught squared plus 2gh divided by negative g. There are two solutions. This negative sign can be cancelled, and the solution I keep is the one that makes sense. So I'm going to get vy naught minus plus the square root of vy naught squared plus 2gh. The reason that plus minus becomes minus plus is because I'm dividing both sides by the minus sign. So these are the two solutions for the time. Since vy naught squared plus 2gh is bigger than, square root of that is bigger than vy naught, if I kept the negative sign, that would be a negative time. The negative time actually corresponds to an imaginary world in which the particle started here at negative time, came here at time 0, and then came here at the final time. We're not interested in that mathematical curiosity, so I'll ignore that, and the solution I keep is tf equals vy naught plus the square root of vy naught squared plus 2gh divided by g. Once I know this, I can immediately substitute, and so the final velocity in the y direction is vy naught minus g sub e times tf, and I invite you to show a couple more lines of work that this ends up being negative square root of vy naught squared plus 2gh. So the final velocity as a vector can be written as the x component, which does not change. That's v0 cosine theta. And then you have the thing that we found here, which is v0 squared sine squared theta plus 2gh. And that's the final velocity in this problem.